let's have your attention, please. So I haven't quizzed you guys yet on anything directly related to type 1, type 2 errors in power yet. They've come up as possible answers, but they actually really haven't been quizzed yet. You can expect next class to have quiz questions that do cover those ideas. And we'll go through section 7.2, which we're about to talk about here soon. But we need to finish the problem that we ended with in lecture A. What did we just do? We just found a 95% confidence interval to estimate the mean weight of all male runners. We got this. We're about to do a hypothesis test that's going to again be two-tailed because we're wondering, is the population mean really 61.3 or not? And actually, since it's a two-tailed test and this interval contains 61.3, I know I'm not going to reject, at least at the 5% level of significance. This was a 95% confidence interval. Alpha, the corresponding alpha is 0.05. At the 5% level of significance, since the null value, 61.3, is inside here, I know I'm going to fail to reject. But let's do the test anyway. Let's see. Do it over here. I've got to calculate what's called the one sample t-statistic with, once again, 23 degrees of freedom. N is 24. N minus 1 is 23. The formula for it is to take the sample mean, subtract the null value, divide by the standard error, S over square root of N. That's the SE thing. Standard error for the sample mean. An estimate for the standard deviation of the sampling distribution of the sample mean. When I say these extra words, it's not just for my own amusement. I'm wanting you to pay attention to all the extra words I say. And when you do problems, it's good to say extra words in your own mind to remind you what things mean. What did we get for x bar? We got 61.9. What's the null value I'm considering? It's 61.3. S, I forgot S. Go back to the spreadsheet. S was 4.85788. Let's approximate it to that. 4.85788. Divide by square root of 24. The top is going to be 0.6. The bottom will be, catch me if you think I make a mistake anywhere, 4.85788. Divide by square root of 24. I get 0.99161. 0.6 divided by that is about 0.605. 0.99161 and then 0.605. That's what I said, right? 0.99161. Okay. So the t-statistic is about 0.6. Not very extreme from 0. The p-value is not going to be very small. It'll be kind of big. We won't reject the null. We do not have sufficient evidence against the null. It's not actually that the null is necessarily right. In fact, with two-tailed tests like this, where the null is that mu equals 61.3 kilograms and the alternative is that it's not, I mean, if you think about that, technically speaking, there's really no chance that the null is exactly right. Okay? Because equals 61.3 exactly, basically there's no chance that that's exactly right. However, that's not the perspective you take with the test. In the test, you assume the null is right until proven otherwise. The question is, do we have strong evidence against the null or not? That's the issue. Not whether the null is really exactly right or not. Anyway, it's a two-tailed test. We've got to double the one-tailed p-value. I'm letting capital T here represent my random variable for the t-distribution 2 times the probability of capital T being bigger than 0.605 with 23 degrees of freedom is the p-value. GF equals 23. And this p-value is going to be fairly large. Two-tailed p-value is what I'm writing here. Equals 2 times the probability of that. With the book, the table, you can only give a range of possible values. We're in the case of 23 degrees of freedom. The t-statistic we got, 0.605, what is it between along this line here? Actually, it's not between any of them. It's to the left of this one. Oops, circled the wrong one. It's to the left of this one. What does that tell you? Well, what the table's telling you now, if you go up to this number up there, since it's labeled upper tail probability and it's an area to the right that's shaded, the table is telling you that a t-distribution with 23 degrees of freedom, the area probability to the right of 0.685 is 0.25. I'll say that again, listen carefully. With 23 degrees of freedom, what this number and this number are combining to say is the area to the right of 0.685 is 0.25. The one-tailed upper area. Since your number, 0.605, is smaller than 0.685, the area to the right of 0.605 is bigger than 25%. Bigger than 0.25. When you double it, you get an answer bigger than 0.5. And that's all you need to say when you're using the table, is this is bigger than 2 times 0.25, it's bigger than 0.5. That's not a good eraser. Oh, yeah, that's the whiteboard eraser. That was probably not good for it. Your two-tailed p-value is bigger ultimately than 0.5. Don't reject the null. We do not have strong evidence against the null. Okay? You never want to use an alpha like 0.5 or 0.6 or 0.7. Way too big, okay? Can't justify that by any means. We definitely do not reject the null here. We do not have sufficient evidence that the population of male runners differs in mean weight from, say, the population mean for everybody, all adult males, if that's the way you want to view it. Can we find the p-value more precisely? Yes, you can with technology. A spreadsheet will work. There's a built-in function you can use. Equals t-DIST. What's the syntax for the inputs? There we go. X degrees of freedom and tails. Okay, the degrees of freedom is n minus 1, 23. Tails is the number of tails. Is it a one-tail test or a two-tail test? We're doing a 2. What's x? X is actually t. They should have labeled it with a t, but they labeled it with an x. So our t statistic is 0.605. That's what goes in first here. 0.605. Comma, degrees of freedom is 23, comma, we're doing a two-tail test. And you can see the answer is 0.55 approximately, bigger than 0.5. And this is not going to change, there's no rand here. 0.5511. Our two-tailed p-value is more closely 0.5511, about 0.55, definitely bigger than 0.5. When you use the book, you can just write this, and it's fine on the homework. It's also fine to be able to write this on tests. You don't have a spreadsheet on a test, can you use your calculator? The answer is yes. You can use a calculator. I don't have the time today to show you what you get with the calculator if you already know X bar and S. We're not gonna, I didn't have the time to type in the numbers and calculate x bar and s. So in this kind of calculator, if I go to my stat menu, where you enter data and where you calculate one variable statistics, and now go over to tests, the first two options it gives me are z-test and t-test. We want to do t-test. Your input for the t-test can either be data or statistics. Data meaning the original numbers, 24 numbers, or statistics, x bar and s, and n. We're going to use statistics. If it was set at data, then set it back to statistics. What's the null value? The null value is 61.3. What did we get for x bar? We got 61.9. What did we get for s? Type it in. Where is it? 4.85788. 4.85788. What do we have for n, the sample size? That's 24. It asks for that rather than the degrees of freedom. And is the test one-tailed, two-tailed, or if it's one-tailed, is it left-tailed or right-tailed? Ours is two-tailed. So now we can just calculate, though you may prefer drawing just to see the area, although I don't know if my window is a good window. I'll just calculate. The p-value, there it is, p, 0.5511 approximately. It's rounding differently than the spreadsheet is. I'm not sure why. But at least they're the same to two decimal places, 0.55. Okay? That's the way you can do it. Actually, it's probably because I rounded x bar when I typed it in there. And I rounded s. That's probably the reason. So you can do that with the calculator as well. So our test ended up not rejecting the null. If we had a different alternative, null value, we could have rejected the null. For example, if the null had been outside the interval that I erased here, then we would have rejected the null at the 5% level of significance. All right, for the rest of the day today, we're going to do another type of problem. Let's see, I'm getting grouped up on my erasers. This one we're learning a lot here. I really did a bad thing a couple of years ago. I was teaching with a whiteboard, and I accidentally used a regular board. I was teaching with a smartboard, and I accidentally used a regular whiteboard marker on the smartboard. That was really bad. So I've avoided smartboards ever since. All right, take a look at that problem. The U.S. Department of Agriculture uses a sample survey to compare wheat prices using independent samples from two different months. July and August we're taking. Here are the summary statistics of the data that they gather, sample data. Sample 1, which would be for July, I should say. The sample size was 32, the sample mean was $7.72 per bushel, and the sample standard deviation was about 25 cents per bushel. For sample 2, for August, the sample size is 27, the sample mean is $7.54 per bushel, and the sample standard deviation is 31 cents per bushel. Question, can we conclude that the national mean prices in July and August are different? All right, so what do we have here? What's the big idea of this setting? You've got these two populations, not one. Wheat prices per bushel in July for all sales of bushels of wheat in the country, and wheat prices per bushel of wheat in August for all sales in the whole country. Those are your two populations. You'd like to know the means of those populations, and are those means different or the same? Now when I say the same, in reality they're unlikely to be, almost impossible to be exactly the same, But the null hypothesis will give the sameness the benefit of the doubt, and you will only try to assess evidence against that assumption, just like we did, I talked about 5 minutes ago. You're going to take 2 samples, one in July, one in August. That's what happened here. Random samples, assumed to be independent of each other. You've got data about sales in some computer, you take random samples in both cases. Now, if you had data about all the sales, you really wouldn't need to do sampling, and there would be no issue about the inference we're about to do. So we're kind of assuming we don't have data about all the sales. We just have data about a random sample in each case. And they're independent. That independent assumption is actually crucial for making the math modeling work. Where have we used independence before? In probability, independent events, the multiplication rule worked. A simpler multiplication rule at least. We also use independence back when we studied random variables in general and talked about the variance and standard deviation of the sum of 2 variables, x plus y, or the difference, x minus y. It's that perspective where the independence is going to be important here. Unrelated is the intuition behind that. And if you're doing random sampling each month, it should make some intuitive sense that those samples will be independent of each other. You've got 2 means, well, 2 sample sizes, 2 means, 2 standard deviations, because there are 2 samples. We'll label whether it's sample 1 or sample 2 with a subscript. This 32 here is N1, sample size for sample 1. This $7.72 per bushel here, that's X1 bar. $0.25 per bushel, that's S1. 27 for sample 2, that's N2. 754, that's X2 bar. $0.31, that's S2. Those are our sample statistics. X1 bar is certainly different from X2 bar, as to be expected. But is that difference statistically significant? Is it enough to give us strong evidence against the null hypothesis that mu1 and mu2 are equal? And that would be the non-alternative hypothesis. Is mu1 equal to mu2 or not? Technically speaking, I should define these parameters ahead of time. For the sake of time, I'm not. On your homework, you should. That's an important step for understanding what you're doing. It's not just busy work. You should say something like this, and you might want to write this down. Let mu1 be the mean price of a bushel of wheat for all sales in the US during July. The true mean population price. Let mu2 be the mean price in dollars per bushel for all sales in August in the country. The population parameters, unknown population parameters, I'm wondering, are they equal or not? Do I have sufficient evidence against the assumption of equality or not? Statistically significant evidence. To do this test, it's equivalent to think about it this way. Are these equal? Well, they would be equal if their difference was 0. Are they not equal? They'd be not equal if their difference was not 0. So what I'm doing here by rewriting these hypotheses in a new form is it's going to allow me to focus on just calculating one statistic and using one standard error ultimately, instead of 2 statistics, and which I've already done, and just comparing them in some other way. We're going to take the difference, x1 bar minus x2 bar. as our point estimate for mu1 minus mu2. It will be different from 0. But is the difference statistically significant or not? That's our point estimate. Right on the board for that one. Point estimate for mu1 minus mu2 is x1 bar minus x2 bar. Very logical. Turns out to be unbiased as well. $7.72 minus $7.54, which is $0.18, in other words, 18 cents per bushel. I'll just write it dollars. It is per bushel. It's certainly not 0, but is it far enough away from 0 to be statistically significant evidence that the population difference is not 0? What does the margin, what does the confidence interval look like first? Let's do that. Since this is a two-tailed test, we can effectively do the test with a confidence interval again. It'll again be an estimate plus or minus a margin of error, our point estimate. x1 bar minus x2 bar. That's what goes here. 0.18. What's the margin of error? It still takes the same general form, a special number times a standard error. The special number is still a t, which we label t star. The star just means special for our book's notation. Other books use different notations, but our book tries to keep it simple and just tries to emphasize it's a star. What standard error do I multiply by? It's not the standard error for x bar. It's not s over square root of n. It's not s1 over square root of n1. Turns out to be more complicated. It's a standard error for the sampling distribution of the difference of these two random variables, those two statistics, x1 bar minus x2 bar. That difference can be thought of as a random variable and have a sampling distribution. What is an approximation for? It's supposed to be an approximation for the standard deviation of the sampling distribution. Here's where the independence assumption comes into play. If you were to find the variance of the sampling distribution for x1 bar minus x2 bar, the assumption of independence would imply that this variance is the sum of the variance of each individual variable. We did use this equation before, back in chapter 4. We used it when we were thinking about, well, the book's example was Derek and Tamara, the shopping associates. I might have labeled them Bobby and Cindy or something. Brady Bunch. Or maybe Greg and Marcia. If you've ever heard of the Brady Bunch before. We used the assumption of independence. This was a minus, this was a plus. That wasn't a typo. This came up on the first test, actually. You used this one. Might have been a plus there for the test, though. We were also using this for the example with the, I believe we were using it for the example with the production process. There was the planning stage and then the implementing stage for some production of some product in an industry. We use that formula. That's going to mean if I solve for the standard deviation that I take the square root of this sum. And remember, I emphasized here that's not the same as the sum of the standard deviations. Basically, this formula can be used with your estimates for these variances to say that that standard error that we're after, standard error of x1 bar minus x2 bar, is the square root of s1 squared divided by n1 plus s2 squared divided by n2. These are means based on sample sizes, so you need the n1s and n2s in there. You know, the standard deviation of the sampling distribution of x bar is sigma over square root of n, which is approximated by s over square root of n. And so for the variance, you could approximate that by s squared over n. That's essentially what we're using here for both of these samples. Essentially using this approximation here and here. And plugging in from there and there as an approximation. That's the standard error. That's what goes here. You can see it's a more complicated kind of formula. Definitely, it's easy to make a mistake when you're using it. So we plug the numbers in. Doesn't tell you what confidence level you want here. Let's go ahead and use 95% confidence. We're doing 95% confidence interval, which for a test is going to mean alpha is 0.05 for the corresponding test, if you do the test. 95% confidence interval, the degrees of freedom, okay, what's that here? Is it n1 minus 1? Is it n2 minus 1? Neither? Actually, it is neither. There's a super duper complicated formula in the book. Doesn't that sound exciting? On page 426, if you want to glance there, called the Smith-Satterthwaite formula for estimating the degrees of freedom in this situation. If you look on that page, 426, you do see it is super duper complicated. Who would ever want to use that formula? Tell you what, not me. I don't like using that formula. It's too complicated. It's too easy to make a mistake. Now you can use the spreadsheet. You can use software to figure out the degrees of freedom and ultimately the p-value. But for doing it by hand and on tests with only a table, and that's all I'm assuming you can do. I'm not assuming your calculator can do what I just did 5 to 10 minutes ago. For doing it on a test with a table, we're going to be satisfied with something simpler. We're going to use the degrees of freedom that is the smaller, the minimum of n1 minus 1 and n2 minus 1. Whichever one's smaller. n1 here is 32. n2 is 27. 32 minus 1 is 31. 27 minus 1 is 26. Use 26. It's not as accurate as the Smith-Satterthwaite formula in terms of giving us the most accurate kind of confidence interval and the most accurate p-value. But that's okay. It does play it conservative. I don't mean conservative versus liberal. I mean conservative as in playing it safe. What does it mean to play it safe? In the context of a confidence interval, you get a bigger margin of error than you necessarily need, a bigger interval for the same level of confidence. So in actuality, you probably can be more confident in your interval than 95%. But we'll still say it's a 95% confidence interval. And for hypothesis testing, it means you get a bigger p-value, which makes it harder to reject the null hypothesis, because a bigger p-value might not be less than alpha. That's playing it safe with hypothesis testing. You're making it harder to reject the null. We're going to be satisfied with that. And I think it's always a good practice to play things safe here, okay? Statistics and using statistics in the real world is not a game where you want to play it risky, okay? You might get fired, people might die, okay? You want to give yourself some cushion. You want to have other people agree with you too. You don't want to just be the sole person responsible for it. Anyway, we're going to use 26 degrees of freedom here. 26. Okay, so let's go to the table. Please don't be putting things away before it's time to go. That can be really distracting. We're almost done. We'll just Probably won't finish the calculation here, but we'll talk about what to do. So 26 degrees of freedom, right there. So the T star we need for 95% confidence is right here, 2.056. So now you plug in the numbers. You plug in 2.056, excuse me, for T star. You plug in S1, S2, N1, N2 in here. Calculate this value. Don't make a mistake. I will calculate it after class, and I'll tell you the answer over email, over an announcement. Plug it in, multiply, get the answer for the margin of error. Then also write it in interval notation. And see whether the interval contains 0 or not. That's the key. For confidence intervals on the difference, the question is, does it contain 0 or not? If it does, then you do not reject the null hypothesis that they're the same. You don't have strong evidence against it. If it does not contain 0, if it contains, in this case, all positive numbers, no negative numbers, then you do have strong evidence against the null, and you would reject the null. So again, after class, I will go ahead and do that computation, and I'll send you the answer. See you next time.